at the beginning, just let me say that we have a very, very great pleasure to say that despite model-driven approaches in system development is a small workshop, we have a regular paper from this workshop technical session, which is declared as the best paper of the whole FETSIS event. So I will share a certificate for this, and I think that you can see it now. Can you see? So the paper Beyond Low-Code Development, Marrying Requirements Models and Knowledge Representations by Kamil Rybiński and Michał Śmiałek is declared as the best paper of the whole conference. And I give my honest congratulations to the authors of this paper. And Dominic, please, would you like to say a little bit more about criteria and how FETSIS come to that decision now, for which we are very happy?
Yes, let me start by congratulating the authors also on behalf of the FETSIS conference series chairs. This is a really fantastic paper, I must say. As about the process, as you can see on the conference homepage, we have special Zdzisław Pawlak awards in different categories. The most prestigious category is Best Paper. We have also Industry Cooperation Award, we have Young Researcher Award, we have International Cooperation Award, but Best Paper is the best paper. This is the most important. This is the most important certificate. What about the process? The process of choosing the best paper is the following. First of all chairs of tracks and technical sessions send their recommendations to the award committee. And then the award committee, consisting of 10 very distinguished scientists, looks at all papers in all categories and votes for the best paper. And this particular paper by Kamil Rybiński and Michał Śmiałek received most of the votes from the award committee, so the decision was pretty clear that it should be awarded with the best paper. So Michał, I heard that you are with us, so congratulations. I'm not sure whether Kamil is also online.
Yes, Kamil is also here. He's not as a panelist, he's as a participant.
Okay, Kamil, so also congratulations for you. We will be in touch with both of you with respect to the details of the awards, because it's not only diploma, it's also some financial gratitude sponsored by PTI and QED Software Company as two sponsors. So we will be in touch with respect to the details, but for now, the most important thing is to acknowledge you and congratulate you one more time. Really fantastic paper.
Yes, thank you very much. It's really a surprise for us, and yeah, we're very happy about that. So thanks a lot, and hopefully we will be able to present it, the paper now during the session.
Thanks, Michał.
Okay, thank you, and hello again. So yes, so what me and Kamil have done was, or mostly Kamil, I was the second author here, was developing a language that we think is beyond low-code development because it marries requirements model and knowledge representations. So let's start with some outline of what I will be. Can you see it? Sorry, because I've heard something.
Yes, it's okay.
Okay, sorry. So let's go for the outline. So first of all, I will give some introduction and the requirements for the language. Then I will present the language structure, and also structure meaning the syntax mostly of the language. Then the semantics of the language. that will be explained translationally, and I will then present some example of code generation, how the code can be generated from these models. And finally, I will present some validation experiments, or maybe just cases that we have done to validate the language. And I will conclude with a summary. So let's start with introducing the language and introducing the idea and the requirements for the language. So first of all, the idea is that we would like to process automatically models that are at the requirements level, that are traditionally treated as part of requirement specification. So these are like, for example, use case models, some activity diagrams or scenarios for use cases, plus the domain model that is also accompanying the requirement specification as part of it, as a kind of a vocabulary of the domain. So these would be the source models, and our ultimate goal would be to be able to generate meaningful and working code that would fulfill certain functional requirements, and that would also fulfill certain rules that are defined in the domain model, certain domain rules. And for that, we would need to develop some transformation, but obviously this transformation would need to be compatible with certain semantic rules. So the source model would need to be given some semantics on how it would be translated into this code. So what is the context of our research? First of all, we have various representations or approaches to represent domain knowledge. So we have ontology specification languages, and we also have modeling languages. That's the first thing, the first part of the context. The second part is the low-code paradigm, or approach, or trend, where we would like to generate most of the application logic and the view of the system, or the front end of the system, from high-level models, from visual specifications. The third element of the context is the Red Seats system and the RSL language. RSL is short for Requirement Specification Language. It has been developed by us in a project that was before this low-code has started. This low-code movement has started. But we think that this can be well treated as a low-code solution because it is based on models that are at high level of abstraction at the requirements level, and they can be translated into these front-end parts of the final code. So the ultimate goal would be to create a solution that facilitates this specification of knowledge, and at the same time, that would be understandable to ordinary people, to the users at the requirements level, and at the same time provide the basis for generation of code from this knowledge expressed using models. To somehow also explain the context, we have these two approaches: modeling languages and ontology specification languages. And modeling languages use these domain models like class diagrams to present some reflection of the reality, of some selected aspects of reality. And the goal is to present this in a more understandable way to people. And the application is just facilitate communication, understanding, and so on. But also used as vocabulary specifications and such. Then we have these ontology specification languages that represent knowledge formally as a set of rules, as a set of concepts, and so on. And the goal is to present knowledge in a way that is processable by computers, by certain reasoning systems, for example. And the application is to be able to infer certain facts from the accumulated knowledge. So obviously, modeling languages are represented usually in a visual diagrammatic form. Ontology specification languages express the rules usually in a textual form as a set of some expressions that define the rules about the real world, let's say. So based on that, we would like to develop a new language that has certain that we would like to formulate some requirements for that language. First of all, we want to represent the problem domain in a way that is possible to be processed by computers to automate this processing. Second of all, we would like this specification to be reusable. And we want it to be compatible with typical requirement specification notations. And in our case, we have used the notation that we have developed, which is the RSL, and wanted to extend this notation. So the goal would be to present knowledge that can be, first of all, understood by people, that discussions between domain experts and computer experts would be facilitated, and at the same time these representations would be processable by translators and so on. So the application of this would be to generate code that would implement the backend part, the domain logic or the backend part of the system. That would be easily integrated with the front end that would be generated using previous methods. In RSL, it's just generating the front end from use case specifications and scenarios and simple domain models also. Okay, so now let's move to the structure of the language, of this new language that fulfills these requirements, we claim. So we're in this first part, which is the source model. First of all, we have RSL, which is the basis. It was developed some time ago already in the previous project. And this is an example model of in RSL, which is quite resembling a typical requirement specification with the use case with the use case model. For each use case, we can specify in a formal way, but at the same time understandable to ordinary users using subject, verb, object sentences. We define scenarios, and then we have the domain model, which is more or less a class model or something around the class model or class diagrams. So now, but from this kind of models, we are not able to generate the backend, the domain logic, data processing operations, calculations, computations, and so on. We can generate the front end. The application logic, which is the interaction between the user and the system. We can also even generate some user interface elements. So the front end can be generated from this, but then we want to extend it. So this is what we report in this paper, which is the extension to RSL, which is RSL-DL, RSL domain logic. It extends RSL with more detailed representation of knowledge of various rules about the of knowledge about the domain, more rules or more details about the rules of the domain. The abstract syntax is defined typically as a meta model expressed in a meta object facility. So it's quite standard. Just an illustration of this. For example, here we have one element of the new language. This is the concrete syntax, this kind of shape, and then we have in the meta model. This shape is a domain logic relationship. This is a relationship. So in meta model we have a meta class, a DL relationship. We have also relationship participants, and these are represented by these rectangles, and we have notions. Specific types of participants are notions, and we have also another type of participant, which is a primitive. A primitive is this oval shape, and all of these participants have to be related to the relationship through relationship participation. Which is denoted by these arrows, so they are directed. So this is just a short illustration of how we define the language, which is quite elementary, obviously. And now, just to go into more details of the language. So first of all, we have certain types of relationships that express the domain. So we have references, which are expressed by the meta class DL reference. References based on data. So here's an example of a reference based on data. It is parenthood, which is based on that we have a single father and a single mother, and they are of specific sex and so on. And the parenthood means that these two persons can have children, and that's parenthood, a relationship. Then we have references based on formulas and equations. So this is this siblings relationship. So there are some additional requirements for two persons to be siblings, which are not expressed in the diagram here. They have to be expressed through additional formulas and equations that are hidden, but can be obviously shown. So another type of relationship is a transition in our language, and first are transitions based on formulas and equations, just like the previous one was also based on formulas and equations. For example, average speed computation is such a transition relationship, which is related to movement duration, average speed, and distance, and it's also is in the context of some movement. And obviously we would need to have an additional formula which is inside this transition that calculates this average speed. Transitions described by full algorithms, they are also more complex, like for example bubble sorting transition. So we have on the input we have an elements list, and on the input we have ordered elements list. And obviously we have to define the algorithm, which also can be done as kind of an extension to this diagram. Okay, so these are relationships, and obviously on the diagrams you've seen also other elements. So let's explain also the other elements. First of all, notions. Notions are we can have basically two types of notions. They are entities, which are just typical notions in a domain, like employee, physician, nurse, paramedic. But also we have more nuanced notions, like for example, inferred roles or identities or so on. So obviously I will not go into these details now because we have no time for that. Sorry. Second type of notions are properties. Now in green we have these properties now marked. So for example, seniority, year of employment, salary, medical specialty. Generally, entities are complex elements of the domain that are composed of these properties. So for example, employee has a certain seniority, has a certain year of employment or has a certain salary, and so on. So these are the distinctions. So for example, so entities can be compared to classes, and properties can be compared to attributes in classes, for example. If we compare it to object-oriented paradigm. Obviously these notions have more details that we need to explain. So for example, you've probably noticed that notions have identities. Can be identities. So identity notions are such notions that here these are examples here. So for example, salary is an identity notion, year of employment, medical specialty is also an identity notions that express the inherent attributes of the particular notion. Assigned role is something that can change in time. So, for example, someone can be a physician during his lifetime, but not always. Obviously, it's not an identity thing. It's not always inherently attached to that person, for example. And inferred role are these are roles that are somehow inferred based on some rules. So, for example, entitled to raise is a notion that means that you can be entitled to raise based on certain conditions. There are also template notions. Here we have an example. Employee is a template because we can have various other notions that can be based on this notion. Okay, so we have also certain conditions in our language, like inheritance conditions. Inheritance conditions are generally similar to inheritance relationships in UML, for example, but they are defined as conditions. I will not go into details why we did that. Maybe if there's a question, we can answer that. But this is a decision that was made. We have identity conditions, like for example, quadrilateral has an identity condition of that the number of sides is equal to 4. We have validity conditions. So for example, here we have PESEL number, which is the identification number in Poland, and validity condition is that PESEL computed checksum is equal to the PESEL checksum, which is included in the PESEL number. Okay, so that's the basic kind of notation of the language, the visual notation, the concrete notation of the language. I will not present the abstract notation, the meta model. This is we have no time for that. But now let's go to the semantics. So we want to define the semantic rules that would enable the transformation of these kind of models into code. So obviously, there are various ways to define semantics of languages. We have chosen the, I think, most pragmatic way, which is to use translational approach. So we have the source language with some syntax. I've presented it just now, the syntax of the language. And we have the target language, and our target language will be Java. So we have the syntax of the language, of course, we know the syntax of Java, and we know the semantics of Java, which is defined in a certain way, and we know what it means when we write some program in Java. And the translational semantics means that we define the rules of how to translate the source language into the target language. And since we know the semantics of the target language, then it also defines the semantics of the source language if we do the translation from syntax of one language to syntax of another language, where the semantics of that other language is known. So whenever a model of program is consistent with some syntax of a source language, then we know how to translate it into the target language. There are various rules that we have developed or Kamil, as the main author, have mostly developed them. And these semantics are described as translational rules from RSLDL to Java. They are formalized in a special language called the MOLA, which is also a model transformation language, but it also in a graphical way allows to explain formalize these kind of rules. And we have developed 16 rules for code generation that cover basically the whole language, and based on these 16 rules we can develop the domain logic code. So for example, we have rule number 10 as an example rule. All the rules can be accessed in the addendum of the paper. Obviously in the paper we did not have space to fit all the rules. There are many of them, as I said, 16, and each of them is well, I will show you the rule number 10 so you can judge. So for example, rule number 10 says that for each reference type relationship, we create a separate method that is called check and then the relationship name in the class that corresponds to that relationship. So we have based on other rules, we have a class that is developed, that is generated from this relationship, but within this this class, we have to create a method like this, check the relationship name. The method has parameters corresponding to all the notions participating in the relationship, and it returns a Boolean value. So this is a rule explained in kind of informal way, but we have formalized it, and here we have the formal well, part of it. It's just a part of formalization of this rule that actually presents a procedure for generating this method in the class from a specific relationship. So here, this is the MOLA language, and I have no time to explain it. So sorry. Just I will show you just without much explanation. I will refer you to the paper for more details. Okay, so finally an example. So how this transformation generating code works. We have the RSLDL model and the RSL model, and they together are input to certain inference engine that determines which parts of the RSLDL model have to be processed based on the RSL model, and then this generates certain rules required for domain operations. Then it's also run through a certain symbolic computation library. These transformed rules are determined, which are required for domain operations, and then altogether this determines the domain logic transformation that finally generates the domain logic code. On the other side, from RSL model, we have also another type of transformation that was developed previously, and this generates the UI and application logic code, and together they combined, they can give the full system code. So here is an example. We have a relationship that is called current academic year. So we want to calculate the current academic year, and for example, we would like to determine whether the current year is the current academic year or is it not. We have the academic year, we have the beginning date, the end date, and the semester change date when the semester changes from one to another. And here we have a current date primitive. So based on the current date, we can determine whether the current date is the current academic year date or not. So are we within the current academic year or not? So here we have some code that is generated, and as you can see, we have this procedure that is called check and then current academic year, which is consistent with this rule number 10 that I've shown previously. So because the rule says that we have to generate a rule called check and then the name of the of the relationship, which is called current academic year. This procedure that was generated using this and other rules, because it just says that we have to generate this rule, but the contents of this rule, of this method, is generated using other rules. This code tells us whether the current year is the current academic year, actually. Okay, so and finally, maybe quickly some words about the validation. We have used two approaches. We have made a questionnaire for students that were taught the language in for 1 hour, and then they had 2 hours to play with the tool for the language. And we also made a validation of operability of the language, which means how efficient would be to develop applications using the language. Well, validation of understandability have shown that syntax understanding after just 1 hour of explanations to the students, which were totally not aware of the language before, was quite good. There are some nuanced understanding that would need to be taught more during maybe additional classes, but after 1 hour they might not grasp everything. But generally we think that language is relatively understandable even after a short introduction. So most problems are with understanding the rows of notions, this inferred rows, and so on. And the second way is the second approach was to validate operability, and here we have this was quite simple, rather anecdotal validation, because we have 3 people: the author, a PhD student, and an undergraduate student, that where we have measured the time where they developed certain tasks, and it have shown that, for example, here in most cases, developing a system using RSLDL was faster, but for example, this undergraduate student made it much slower than he would do it in Java, because he was experienced in Java. He was not experiences in RSLDL. The PhD student was less experienced in Java, so it took him more time. So obviously this is just anecdotal. We would need to do much more research on that. But even with these results, we can initially argue that as general knowledge of developers and their skills in RSLDL rise, their productivity would rise significantly in compared to developing this code in pure Java. So generally that's it. I'm not onto long summaries, so just a short. As for summary, we can claim that this declarative, because this is a declarative language, declarative knowledge representations can be used to produce third-generation language like Java backend code with non-trivial domain logic. It's not trivial. The logic can be quite complex. And there are 2 potential areas: reduction of complexity, obviously, and also reuse, which I didn't mention much, but these kind of models can be reused quite easily. Okay, thank you, and I'm waiting for questions.
Thank you very much, Michał, for your really interesting presentation. I can say very huge work of a very wide solution for many classes of problems, and I think that it raises the quality of your approach. So please, your questions now. I have one also. So as I'm a guy coming from the area of databases and generating database structures and also business logic at the level of database, and we had some similar, let's say, endeavors to develop such languages. So my question is how you can use your RSLDL for describing complex database operations in the background, keeping in mind that apart from classical CRUD operations, you have always some batch jobs with very complex logic inside of calculating something of selecting so much data, then creating some intermediate files and so on. So can you use your system in that problem domain?
Okay, so your question was a bit breaking the voice, so but I think I understood most of it.
If you like, I can repeat here.
So I understand that you would like to know about the how would it be applicable to also generating some database
logic.
kind of. Sorry?
Yeah, in the background, database logic of some batch applications, not only typical interactive CRUD applications, just performing basic operations, but you have, for example, calculation of salaries. It's a typical batch that is performed once or twice a month, and it's with very complex calculations inside, and maybe creating some different intermediate files and so on. Can you specify it in an independent way and then to generate that kind of logic?
Yes. Basically, the CRUD operations could be generated from already from RSL without the DL extension, because this is very simple. But here we concentrated on the approach where the domain logic is in the kind of domain logic layer, and the database realizes simple CRUD operations. So we're not, we did not assume generating code that is embedded in the databases, for example, but rather it's outside of the database, like developed in Java, let's say, and it also connects to the database to realize these CRUD operations. But obviously, if we would develop some additional rules, then I think it would be possible.
Yeah. Why? Because this is not just business logic on the middle layer, but it is a logic that is going on the level of DBMS. So it's important then, because it's a natural place where such kind of operations are performed.
Did you? I'm not sure, because unfortunately there are some breaks in the. Did you mention BPMN or?
No. Just I mentioned that, okay, you mostly are concentrated on a business logic on a middle layer in your applications, but sometimes you have very heavy operations on data that should be placed at the level of DBMS. Why? Because application layer with business logic is not powerful enough to complete those operations. It's a natural database for that.
Yes. So obviously, but as I said, if we add additional rules to that, and then we would like to place this logic within the database management system, then obviously we could do that.
And another question, also in some data-intensive applications with user-intensive communication with such system, you have so much options for generating user interface forms and layouting your fields and to adopt some logic for user interface. Can you do that with RSL language also?
This is previous work, but in RSL we generate forms, but they have standard layout.
Standard, yeah.
If we have like a notion with 5 attributes, then that's more complex, but then we have 5 fields that are like layouted quite standard. But
I agree with you. As I have same experiences, it's very complex. So much properties you must have in your plan to do that. So we tried that, and it was nice attempt, but yes, it's very, very demanding. Thank you very much again for your really nice paper.